Hello, hello boys. Let us today look into the inorganic polymers. So I think you have already studied about some catalyst in the organometallics. So here are certain things that pertain to the organometallics. Here this one is there. So Ziegler-Natta catalyst. I think you have had this. And this features, this subject should contain everything about the metal complexes that lead to polymerization, and I should be able to describe the mechanism of catalyzed Ziegler-Natta catalyst ring opening, and sometimes like atactic, isotactic, synaptic. This is not in your syllabus, but it must be there. It should have been there. Then ring opening mechanism of this, and that comes under the polysulfur nitride. Uh, and you should understand the concept of particularly the charge transfer complexes. It is very important there. Some common inorganic polymers like silicates and zeolites are also needed very importantly. And then how simple coordination polymer structures can be built from combination of metal ions and organic linkers. So this is an organic and inorganic polymer. It's a combined one that is also there. So some books are there that is given there. So I just taken the books. You can just refer, pause it and note the books there. And, I think one of the best books that you can see on polymers is this Metallurgians Introduction to Sandwich Complexes by J. Long, Blackwell Science. And then this one is also very good. So you can refer there. So now let us come to this what I am going to cover. So here we are not going to cover this synthesis mechanism. We're just I already dealt with the Ziegler-Natta catalyst to prepare the polyethylene and polypropylene. I think you have studied them, and I told you under the polymerization. Then ring opening is also there, but this is also not we're seeing. So main thing we are going to see is this polysiloxanes, polysilanes, and polyphosphazines, and some transition metal containing complexes. Is just a brief way to look into what the synthesis is there. And if possible, I just look into the organometallic magnets also, and then metal coordination polymers also is there. Okay, so now let us move over to what this metal catalyzed reactions means. Here, I think you know about this polymerization is oligomerization, that also you have seen in the organometallics. Here, alkene polymerization and ring opening metathesis polymerization is there. Now there will be separate units in the oligomerization. So these units will keep repeating, unlike polymers in organic where you have only these particular units. Like for example, only alkenes are there, so you have CH2 there, or CH3 there, and then CS2, 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 CS2 like that. So just goes on to get polymerized, and some rearrangement there of course. And in the oligomerization, you can have some units like for example SiO4 tetrahedra or Si2O7 dual tetrahedra that gets repeated in a particular unit. That's what you call it as the oligomerization. So this one of the best example for oligomerization is found in the Ziegler-Natta catalyst in the organometallic chemistry. So the difference between isomerization and oligomerization is very clearly given here. You can see that in the oligomerization. So three units are being used there, and these are getting repeated, and some ring opening, some bond deformation and formation of some other bonds is also there. So that is what is mentioned there. So you have to take care of what is meant by oligomerization, what is meant by isomerization. Isomerization is the same units, just the change in the double bond system from position 1 to position 2, 3, 4, and then position 5 like that. So the change in the double bond position will be called as the isomerization. And in a metathesis, you have seen that it is just changing the geometry. So that is also a kind of isomer. So look at what is happening at the polymerization. You have got n times that alkyl groups that is getting repeated, and there also is a CC bond formation. Of course, we are not going to look into the ring opening metathesis. So I'm just briefly telling you about the inorganic polymers, how they are useful. And that aside, it was the Ziegler-Natta catalyst that we often see as that used for a very essential catalyst that is being used for the polymerization of ethanes to linear polyethylene at room temperature. And here is it, that nomenclature is there. Just for your information, I'm just telling that's adjacent stereocenters have random configuration, will be called as the atactic, isotactic, atactic. Whenever you use the word A, it is just opposite of this. Isotactic is adjectives have same configuration. Look at this, here it changes. This one is different from this one. But here you have got all of them similar like that, so that will be called as the isotactic. So these two terms are enough for you, but just have a glance at what is symbiotic. Adjacent stereocenters are opposite. So this are the opposite configuration. Stereo block, you got one complete block like this and then another block like this. So by the use of TaCl4 and aluminum triethoxide, ethylene, triethylene, and that is low, and polydispersity is high depending on the type of preparation you are requiring. So in the inorganic polymers, that is of main concern to you is they contain other organic atoms in the chain polymer containing phosphorus. You see the word that is written in the inverted quotes, which means that it is not essentially organic, which we consider as only C and H for the organic. Here you can include them, something like phosphorus and something like nitrogen, etc. Okay, these compounds are of interest because they offer the opportunity to develop new technological applications due to their reactivity, structural and physical properties and essential points. Many you can pause them and take the notes from these sections, and many are known. The most widely used developed is the silicon, polysiloxane, polysilane is there. This one, SiO. So I think you have heard of the silicones also, and then silicates is a difference where you have this type of compound with an organic like structure, you get silicones, and then here you have got this without oxygen is there, so that also gets repeated. With the inclusion of phosphor is there, phosphor and nitrogen is there, that is what compound that we use, we call it as the polysilanes. So most important inorganic polymers with regard to commercial applications like catheters, prosthetics, that is some nurse catheter, so where you want to put certain nuts, cutty powder. Okay, so contact lenses. I think some of this will have this chitin molecule also, that is a polymer again, and that is also being prepared by the same catalysts. And then drug delivery capsules are there. There are many capsules, they deliver the drug and they come out of the body. So drug delivery capsules, catheters, prosthetics. Prosthetics, is, for example, I can just tell you some prosthetic fingers are there, something damaged, and then you just replace it with some. And nowadays they are using the sutures, okay, surgical sutures. What is for stitching, they use a kind of thread that also is a kind of decomposable polymer that doesn't contain any silicon but has got organic compounds which can openly decompose over time, or you can even simply remove it because they are less stable, or you can call it as the biodegradable, and they are used for non-medical applications also, such as elastomers, adhesives, lubricants, water repellents, molds, and cosmetics. I think you know all the terms, but very important thing is the adhesives and lubricants. So most times, silica gel is very widely used, is very widely applied. So nowadays you have some uh, water stopping tapes on there. So that is also a kind of elastomer. So you look at this preparation. This method is important for you. Silicon reacting with an alkyl chloride 2 moles of alkyl will give R2 SiCl2, and that when treated with water in the presence of HCl will give a polymer that is having twice that of the alkyl things with the SiO. So this is a polysiloxane. Siloxane. Okay, so here is then you're using the catalyst there, ring opening polymerization takes place, and the same thing is there. Okay, but still further polymerization is being done. So here another route is given that may not be very important to you, but just is there. It is given there. Polydimethyl siloxane is the most widely used thing they are telling. I'll look at the next part of this preparation. Two general methods, the condensation and dichlorosilanes with alkali metals, can also give rise to some polymers. R dash SiCl. That gives in the presence of sodium and toluene RrSiN. So here it is chlorine is being removed. Chlorine is being removed. So these are the presence of sodium, so it forms a sodium chloride. Product distribution indicates radicals as important inhibitors. So they have found that radicals are important intermediates there. So where can you start from? R dash B SiCl is there. So in the presence of sodium, okay, you get a salt like this, sodium plus and minus, then another chlorine. Both the chlorine is removed, and then you get the silicon or like that. So you can see that this chlorine is removed. Then further you put sodium, then you get another salt, and then you add up one more molecule of this one there, then you get a polymer like this. So very good polymer. So Si. So this unit is one polymer already, but you can repeat them. You can repeat them to get. So in the examination, you have to write this reaction is very important thing. So I think it's not much difficult. You can write any silicon and forget about the chlorine atom there. So it is mentioned as a dehydrogenative coupling of silanes. So NRRSH2 is a catalyst. So you get two hydrogen atoms on both sides, and then minus one H2. Two proposed mechanisms are there, not needed for you. But you can have a look at how the titanium is acting as a catalyst in framing out this SiS2R. Okay, so not essential to you. And then this sigma bond synthesis is given there. So this is also not part of your curriculum meta thesis. So I'll just skip this also. But you can see the properties of the uh, general polysilanes. So what does it say about the general polysilane? It says sigma electron delocalization is present in, it's a very huge thing. Okay, so usually you see pi electron delocalization in benzene atoms or something like that, but this one is a different thing. So you get a sigma electron delocalization that contains organic polymers, e.g. polystyrene, that have pi electron delocalization. So physical properties arising from delocalization includes strong electronic absorption, conductivity, photoconductivity, and photosynthesis. So it is having, you can see that some electrical and optical properties are also there for these things. So optical fibers you can make. So sigma electron delocalization occurs primarily because of the good overlap of Si bonds and lower electronegativity of S relative to the carbon atom. So a very essential thing is the electronic description of the mini atom materials can be described using band theory. I think this we have seen, the band theory of conductors we have already seen, and if you ask me, I can put it number n times important, because you have to understand the uh, molecular orbital concept of in terms of the bond theory, in terms of the MO theory. The MO theory is the most successful one. So if you plot it in terms of the energy, you get bonding and anti-bonding orbital there. These two things, bonding and anti-bonding orbital. And then when you have the many hydrogen atoms, so you can just put all the bonding levels like this and then anti-bonding levels like this. And when you have such close levels, so that means, if you have an electron here, it is lower in energy, this electron is higher in energy, but they are within a particular framework, within a particular value, so they can just overlap. And so when they just overlap, we just call them as the bands there. We just call them as bands. Okay. So in the bands, you got the free movement of electrons, free electron movement. We have seen in the band theory of conductors, and I have told you about the Fermi levels. So the Fermi level is the level where electrons can move free about. Is also it is not a band. How it is different from a band? In a band, you have all the electrons within that particular region levels, but in Fermi, you have got space where the electrons can simply move about. So this is the region. You can just see the extra region there. Okay, this particular region is is a Fermi space within which it can go and come back. Beyond that, if it goes, it can decompose. Okay, so as you put more and more electron, you can see that this band is narrowed into this band. This band is narrowed into this one. Okay, the band gap is getting narrowed. For conduction to occur, a band must be partially filled. You can do this by adding electrons to the conduction band by reaction with a reducing agent. So note this very important point there. By adding reducing agent, you are adding electrons. So actually, with the reducing agent, what is the purpose of reducing agent? What is the concept of oxidizing agent? You must know. Removing electrons from valence bond by reaction with an oxidizing agent. So it is adding electron, and it is adding electron and removing electron in terms of reducing as well as the oxidizing agent, but promoting electrons from the filled valence band to the empty conduction band using heat or light. So this is a concept where when you heat a semiconductor, it becomes a conductor. Okay. So as you put more and more polymers, more and more sigma levels are there. We have seen that there is sigma electron delocalization. This particular concept we have seen here. So that sigma delocalization is taking place here. So much that you can just put up more and more, more and more, and more and more. So and you get a very thinning of this band. So this is called as the band, and the band gap lowering is responsible for the movement of electrons from this to this. So this you call it as the valence band, and this you call it as the conduction band. The other name we often see is anti-bonding and bonding orbitals, but actually in terms of the property, they are called as the conducting band and valence band. So you can promote them always. You can see that here sigma star is a conduction band and sigma is a valence band, but not necessarily the same reverse, but you have just proved it as a band. Okay, and then pertaining to this, we have the uh, Silanes there, right? Here we have. In polysilanes, the band gap is 300 to 400 nanometer. The polysilane is such that 300 to 400 light can exit electrons. That means, so this is the wavelength that they are mentioning. What is this 300? It is just violet. Okay. So a violet color or a small less than ultraviolet color just can excite the electrons from valence band into the conduction band and make it conducting. So it's a very good property. Why? Because you have got some material is there which is not conducting. Okay, but when you put some light like H nu, it becomes conducting. Why? Electrons are getting promoted from the valence band into the conduction band. The band gap is sensitive to chain length. So increase the chain length, you can have these different types of band. Band gap decreases and absorption range increases, lower energy reaches limit of 30 silicon atoms. So conformation of polymer chain, that is, you can have trans and you can have some cis. So you can see the difference between these two. So not within our purview, but still it says that the number of silicon atoms as well as the geometrical conformer of the atom can affect the bond lengths. Okay, so here this is the mechanism that is there. So you have got a photoresistant material and you put some light into that, it becomes and I mean it photoresist. What is happening? It is resisting the electrons. So you are see here you have got some mask which doesn't allow light. So you allow light only at this particular place. Okay, it's an Si wafer. Si wafer means it's a layer which is a very thin layer is there, and then it just cuts out that particular part away from these two. So here is this particular pertaining to this, it just cuts out. Okay, so here this region is cut off. Why? Because it's capable of making conducting, and it's capable of conducting sigma into sigma star. Okay, so property is getting changed there. That is what is mentioned there. And here is the polyphosphazene, largest class of inorganic polymers because of ease of a side group modification. I think you have to remember this polyphosphazene is very important there, and that pertains to this. You have to write the structure simple: P R R double bond N. After writing this PR2N, you just have to extend these two lines and put a square bracket like this, so that it called as N is always greater than 15,000. Backbone is called as the backbone. It comprises alternate P and N atoms. Side groups R can be organic, inorganic, or organometallic. Method of synthesis allows modification of the side groups. Uses include electrolytes, batteries, advanced elastomers, elastic at low temperature, aerospace or automobile applications because of resistance to hydrocarbon solvents, oil, frame, and even textiles, and even many polymers, such things like that. So you need to draw a structure like this. This is very important for you. And here, I think you have heard of this. Is called as something is called as the inorganic benzene also. Okay, you get PCl5 in the presence of NH4Cl or HCl. They just polymerize at about 10 to 50 degrees. So you can see that NPCl5 is NPCl2 three times now. NPCl2 three times, and it's getting like this. But at temperature like this, you get a polymer of n times and then thousands. Okay, so in the place of Cl, if you have this OR, Cl can be substituted in the place of OCS3. You get a OCS3 polymer, and if you have NH2R, you get NHCH3 kind of polymer. So this come under the polyphosphazene, and that is what is very essential for you. You can also functionalize the PN precursor to the polymerization. So here it is. The precursor is something prior to polymerization. So what is happening here? You can see that some of the fluorine atom is substituted by means of the aromatic rings, and this facilitates easier breaking of this particular compounds into this breaking of these compounds because of the higher thing, and you put it, and that breaking is what you call as the ring opening polymerization. So this is a very important reaction for you. You need to remember this. NPCl2 three times in the presence of heat, which gives a phosphocation there, and then two such things combine together, and then one remains like this, and then you have got this polymerization. So cationic, it's called as the cationic chain position. Okay, so what is the bonding? Cis and trans compounds exist, and barrier rotation about PN bond is very small. What is meant by this barrier rotation? Suppose if we have this C double bond, what is that? N double bond P is there. Then you got two Cl atoms up there. Okay. So there is possibility that this P double bond can be rotated over. Okay. But if you have a Cl here, rotation becomes restricted. So this is talking about the barrier cis and trans conformance barrier rotation is very small. Therefore, you can keep on rotating. However, the bonding in phosphorus is still not understood. So theories have been discussed since 1960, but it's not still clear how these things, the cis and trans isomer have the same type of properties. So generally, the empirical properties suggest that alternating bond lengths, but the bond length is much alternating bond lengths, but the bond length is much less than a single PN and a multiple bond character. So empirical means just from some other analysis of the chemistry. So already we have seen how empirical methods, ab initio methods are impacting our study into that. So here is the very important part of your syllabus. NPCl2 3 times the polyphosphazene is given there. This is the structure there, polyphosphazene. They are not colored and do not conduct electricity. That is a characteristic of extensive conjugation. So here you have that the sigma framework is there. The problem is distribution of the remaining valence electrons. Derive proposed a phosphorus 3d orbitals. Do you have the 3d orbitals for the phosphorus? Actually not, but some d orbitals which are empty adjacent to the phosphorus are involved in bonding. So phosphorus having 3d orbitals, you need to concentrate how they are mentioning it. Already I have told you that in some cases hydrogen which is having 1s1 is capable of behaving like hydrogen 1p1 in some cases, rare cases. So just like that, the behavior of these particular unconducting or conducting property can be explained by means of the D character. So that D character is defined here. Okay, actually this P should have been like this, these three, only P orbitals. Okay, but here we are having 3D orbitals there are involved in bonding to give P and P islands where N, P to Z overlap with the PT orbitals. So that makes them very stable. What is it here? These two are very good in symmetry and they just overlap. Here these two are very similar and they overlap. So that makes it very good stable. So rotation about PN bond is low energy because P to Z can retain overlap with 3D orbitals on rotation. It's a very good theory. What it says is actually, if you have these two, the rotation should not be allowed. Rotation not allowed. Okay. But what happens? Because you're having d orbitals can be so liberal that you can rotate them. At one point of time, you can have this going like this and this coming like this. Therefore, this coming like this and this also coming like this to overlap the required symmetry overlapping there. So it's a very good theory suggested by Dewar. You need to understand the molecular constants. Some more recent calculus suggests that ionic bonding appears to be dominant. So this is the final structure of this NPR2 of the polyphosphazene. You can write both, but this one is also very prevalent there. More so because you have got two non-bonding electrons of the nitrogen, and nitrogen quickly because of its lone pair is a kind of nucleophile and has got retains its electron there. Phosphorus, which is hypervalent, is capable of retaining this plus charge. So this is a very good structure. So these two structures are very important. I suggest that you look into this and understand what 3D orbitals or rotation means and how the structure is stabilized despite the concept that cis and trans conformers are having the same stability where they should not happen. Okay, so I think we have come to the general conclusion of how the inorganic polymers are there. So one of the best example is the Ziegler-Natta catalyst used in oligomerization. That is also a kind of polymers, inorganic polymer. But there are more organic atoms involved. Here you use the silicon and phosphorus, and some methods are there. So you need to remove the electrical properties due to the band gap shortening there. And then the stability of certain inorganic polymers is because of the some adjacent empty orbitals that are not actually the part of the particular atom. For example, 3d orbital is not part of the phosphorus, but they come into play when you have got certain polymers because of the energy level rise, and that is the next energy level after P is D. So when P's energy is rise, it matches with that of the D, and therefore it's a functionality comes to the core. So you need to remember wherever I have put these important marks, you just look into that, note that particular points, and write those things up in the examination. Let's see you next part of that in the next class. Thank you for joining.